Hello. So today we're going to be talking a little bit about electromagnetism and specifically how we use the right hand grip rule in this context. So we're going to start off with our first situation, which is number one. What happens when we have a current flowing through a straight conductor? And so one of the things that we should be aware of is that whenever we have a current going through a straight conductor, a magnetic field is made around the straight wire. So when we want to figure out the properties of, or specifically the direction of either the current or the magnetic field, we're going to need at least one of those to figure out the other. And for this, we can use the right hand rule. And it's something like this. Let's make this a little bit bigger. This, our thumb over here is going to represent the straight wire, and specifically the direction that our thumb is pointing represents the direction of the current. The four fingers we have over here are going to direct or are going to show the direction of our magnetic field, as you can see over here. And when we hold it up in a thumbs up position, we can either have our thumb going up and thumb going down. And that's going to tell us what that magnetic field direction is when we have the current going in that direction. When we have it like this, we also need to be aware of certain factors that are going to affect the magnetic field strength. One is current, and two is the distance from the wire. So this makes sense because the stronger the current is, if we have lots of or very high current, we're going to have a much stronger much stronger magnetic field. And the direction is still going to be the same, but we can know that it's going to be much stronger and it'll have a stronger magnetic field strength. Similarly, for distance from wire, we know that if you have an object over here, let's do this in a different color. If we have an object over here, versus an object over here, this object is going to experience a much stronger magnetic field strength than the object over here. One thing that we should be aware of is that when we're drawing magnetic fields, these over here need to be perfect circles, and there must be arrows showing the direction of the magnetic field, which is why it's important to be using the right hand grip rule. Oh, I spelled straight wrong. So it's important to be using the right hand grip rule to show the direction of both the current or the magnetic field. And obviously, vice versa, if we know the direction of the magnetic field, but we do not know the direction of the current, we can just use our four fingers to portray the direction of the magnetic field or to show that on your hand. And depending on where your thumb is pointing, either up or down, you can tell what the direction of the current is. The next situation we're going to be talking about where we can use the right hand grip rule is when there's a field due to current in a coil. So this is going to look a little bit different. When we have a current in a coil, one of the things that you should know is that it's going to produce a magnetic field around it. When you have something like this, let's say this is our solenoid, we're going to have a magnetic field over here. And let's say this is our north and our south, and we're going to be, our magnetic field is basically going to start looking something like this, and then we're going to have like little circles that are eventually going to go around the coil. But this is how our magnetic field is going to look. Let's see if I can, something like this. Let's make this a little bit. If that clarifies it a little bit. And so the direction that the current is going in this solenoid is actually quite important to knowing where north and south are. And we can also use the right hand grip rule in this context as well. Over here, our fingers are going to be pointing where the positive charge is going. And the thumb is going to be the direction of the field. So our thumb is going to be pointing towards north. In this situation, if we don't know what direction our current is in this coil, what we can do is point our thumb to the left because that's where our north pole is. And the direction that our four fingers are curling in tells us where where the current in the solenoid is going. When we do this, we can see that actually, because our fingers are going to be pointing that way, we know that, oh, let me do it in a different color actually. We know that the current is going this way. And so we know this has to be positive and this has to be negative because our positive will be going to our negative. So these are the two contexts in which we can use the right hand grip rule. Really quickly before I finish, let's touch on one more thing about fields made due to currents in a coil. We talked about the factors over here that's going to affect the magnetic field strength in a straight conductor. We have the same sort of thing over here. What's going to affect the magnetic field is number one going to be current. We're also going to be affected by the number of coils. And three, the material. Oh, sorry. So we're going to have current and the number of coils, but more specifically, it's actually the density of the coils. How many coils do we have per unit length? And so, for example, if we had two coils that were different lengths but had the same number of coils per unit length, then you're actually going to have the same magnetic field strength. For example, if we have a coil like this and a coil like this, we actually have the number of coils per unit length the same. So it's going to experience no difference in its magnetic field strength. But anyways, these are the two situations where we can use the right hand grip rule in our electromagnetism context. So it's very handy to know, and hope this helps.